When the AC motor is first switched on, there is an initial rush of current that may be 5 times higher than the average running current. In fractional horsepower motors, this momentary high current is usually acceptable, but for larger motors, special provision is usually made to reduce the initial current surge to prevent electrical and mechanical components from being overstrained. Once the motor is running, its speed will be determined by the frequency, which is why the AC motor is usually thought of as a constant speed motor. At one time, controlling an AC motor meant turning it on and off. Currently, this notion of the AC motor being constant speed is being revised because efficient electronic power circuits can vary the frequency, thus allowing the speed to change. This and other topics having to do with motor control are the subjects of the subsequent section. The simplest way to start a fractional horsepower AC motor is to connect it to the line voltage through a switch, and this is how it's done in many cases. These diagrams show two different schematics for this approach. Both schematics are for the same circuit, but figure B is drawn in a form called a ladder diagram and is typical of an industrial motor wiring diagram. In the ladder diagram, figure B, L1 and L2 are the AC line voltages, and each rung is a circuit. The symbol labeled OL in figure B represents the normally closed contacts of the overload device. Normally open contacts would have a diagonal line. The overload device is designed to open its contacts if the motor gets too hot. This device may be a thermal sensor built into the motor that will trigger when a certain temperature is reached, or it may be separate from the motor, in which case it's actually triggered by a sustained current overload condition. The start-stop circuit for motors used in industrial processes is typically a little more complicated than an on-off toggle switch. The motor might well be controlled from a control panel some distance from the motor. In such a case, routing the motor power through a relay located near the motor and running the low current wires, which only need to energize the relay coil to the control panel, makes sense. This approach is particularly appropriate for large motors. An everyday example of this system is the starter motor in a car. When you turn the key, a low current ignition switch provides power to energize a high current capacity relay, starter solenoid, that in turn connects the starter motor to the battery. A relay specially built to start motors is known as a magnetic motor starter or magnetic motor contactor, or more generally a contactor. A starter generally has a contactor and overload device. A magnetic motor starter has large contacts to handle the motor current and often includes built-in current overload device. When the current exceeds some preset value, the contacts open. Besides safety reasons, sealing circuits are useful when the entire plant loses power. When the power is restored, you don't want all the motors starting up at the same time, causing a tremendous current surge in the main power lines. Instead, the motors can be restarted individually or in groups in some orderly fashion. Also, starting and stopping motors from multiple locations is common. For example, a cooling pump in a nuclear power plant may be started from 3 places, for example, the main control room, the pump's site, and the auxiliary control room. This diagram shows the start-stop circuit for a 3-phase motor. This is basically the same as for the single-phase motor, except that the relay now provides 3 sets of contacts for the motor M2, M3, and M4. Also, the motor starter coil circuit, which requires only single-phase AC, is connected across L1 and L2. For larger motors, the coil circuit voltage may be stepped down to 120 volts with a transformer. Jogging refers to applying power to the motor in short bursts for the purpose of inching it into some desired position. For example, a commercial mixer might need to be jogged into a certain position so the blades can be replaced, or a motor driving a large shaft might need to be jogged to get the keyway lined up with the mating part. The traditional motor control circuit discussed in the previous section, which uses a sealing relay, does not lend itself to jogging because it's not responsive enough. That is, it can't cycle on and off fast enough. Jogging requires that you have a direct push-button power control to the motor, which usually means bypassing the regular on-off relay circuit. This diagram shows a simple motor control circuit that has a provision for jogging. When switch A is set to run, the circuit behaves exactly like the circuit previously reviewed. That is, the relay is sealed every time the start button is pushed. However, when the switch A is set to jog, the sealing circuit is disabled. The power is supplied to the motor only when the start button is pushed. The nature of any motor is to have a large initial current when first connected to a voltage source. The power distribution system can usually cope with the increased startup current of fractional horsepower motors, although the lights may dim perceptibly in the immediate area. But larger motors usually need special starting circuits that limit the starting current to some acceptable value. One of the simplest ways to limit startup current is to connect resistors in series with the motor during the startup period. After the motor has come up to speed and is drawing a reduced amount of current, a switching device removes the resistors from the circuit and the motor is connected to the full line voltage. This circuit diagram shows a reduced voltage starting circuit for a three-phase motor. Notice the presence of resistors R1, R2 and R3 in series with the motor power lines. Also notice that each resistor is bypassed by a relay contact. When the start button is pushed, the MR relay coil is energized. In context, MR1, MR2 and MR3 close. This action connects the motor to the power lines, but the current must go through the resistors. Another MR contact, MR5, applies power to the coil of a timer relay, TR, a relay with a built-in delay mechanism based on pneumatics or electronics that causes its contacts to close a certain time after the TR coil is energized. The delay is set to give the motor enough time to come up to near operating speed. When the relay times out, contact TR1 closes and allows relay coil RB to be energized. Relay RB has three sets of contacts, RB1, RB2 and RB3, that connect the motor directly to the power lines, bypassing the resistors. The reduced voltage starting circuit is simple and relatively inexpensive, but it does have the drawback of reducing the motor's startup torque. Remember that torque is proportional to current, and if the current is limited, so is the torque. One way to improve the situation is to use transformers instead of resistors in the startup circuit. The advantage of using transformers, actually auto-transformers, is that they can provide the motor increased current while not straining the power distribution system. The transformers are only engaged during the startup period. When the motor gets up to speed, the transformers are switched out and the motor is powered directly from the power lines. AC motors enjoy many advantages over DC motors. They are lighter in weight, more reliable, less expensive, and require less routine maintenance. And although small speed changes can be made by changing the voltage, AC motors are essentially limited to running at a speed determined by the line frequency. This fact has traditionally kept them from being used in control systems, where the speed needs to be varied. The introduction of high-power solid-state switching circuits has changed this picture. Clearly, if you want to fully control the speed of an AC motor, you must be able to change the frequency. This can be done with off-the-shelf power conversion units that are capable of converting the line voltage at 60 Hz into a wide range of voltages and frequencies. A motor control unit, or a control unit plus the motor, is called a drive. There are 4 choices of AC motor variable speed drives. The older variable frequency drive, known as the V/H drive, and the newer vector drives, sensorless, flux vector, and field-oriented control. The traditional variable frequency drive, known as the volts per hertz drive, changes the motor's frequency and voltage using solid-state control units. The basic steps for this process are shown in a block diagram, and the circuit is known as a DC link converter. The first step is to convert 60 Hz AC into DC power. The second step is to convert this DC power back into AC at the desired frequency. A generalized variable speed control circuit is shown. In this circuit, 60 Hz AC line power is converted to DC with a silicon-controlled rectifier network. SCRs are used so the magnitude of the DC voltage can be controlled. Recall that the SCR is essentially a diode, but in order for it to conduct, 2 conditions must be met. First, it must be forward biased. Second, it must receive a trigger pulse on its gate input. Referring to the circuit, if the gate G of each SCR is pulsed at the beginning of each positive AC cycle, the conduction time will be maximum and the maximum DC voltage will result. If the trigger pulse to the gate is delayed, then the SCR is conducting for a shorter time and a lower DC voltage is established. Note that L and C help smooth out power pulses from the SCRs. To sum up, the average value of the DC voltage can be determined by controlling the delay of the trigger pulses. The next job of this circuit is to create a sort of artificial 3-phase AC power at any desired frequency. This is accomplished with 6 transistors on the right side of the circuit. Each transistor is turned on and off in sequence by a controller circuit, not shown, in such a way as to cause 3 pseudo-sine waves. Figure A shows the simplest 3-phase output voltage waveforms that can be made from this circuit. In particular, notice the phase A voltage waveform. During time period 1, both transistors Q1 and Q2 are off, so the output, which is taken from between the transistors, is neither positive or negative. Then, during time period 2, transistor Q1 is on, connecting the phase A output to the plus DC voltage. During time period 3, both resistors are again off. Finally, during time period 4, transistor Q2 is on, connecting the phase A output to the minus side of the power supply. This same shape waveform is generated by transistor pairs Q3, Q4, and again by Q5, Q6, with each phase lagging the one ahead of it by 120 degrees. Clearly, the apparent frequency of the output is determined by how fast transistors Q1 to Q6 are sequenced, which is typically in the range of 5 to 120 Hz. To help visualize the 3-phase action, compare the phases A, B, and C in figure A with phases A, B, and C in the traditional 3-phase diagram, figure C. A better pseudo-AC waveform can be created by using pulse width modulation, as shown in figure B. For the motor to work well at various speeds, the voltage of the motor must be modified each time the frequency is changed. Specifically, the voltage and frequency should be held proportional, that is, when the frequency is increased, the voltage should be increased and vice versa. The reason for this requirement is that the current in the stator windings must be maintained at certain design value for the magnetic induction process to the rotor to work. Most motors are designed to operate at 60 Hz and 120 volts or 240 volts, so the stator is wound to create the proper magnetic field with these conditions. If the frequency drops below 60 Hz, the inductive impedance of the windings also drop, which would allow in more current. Consequently, the voltage must be lowered as the frequency is lowered in order to maintain the proper stator current. Figure A shows how the voltage should increase linearly with frequency in the range of 0 to 60 Hz and explains why the type of drive is called a volts per Hertz or V/H Z type. The voltage is usually not allowed to increase beyond the motor's rated voltage for its own health. So in practice, there are really two distinct operating ranges. The first range, 5 to 60 Hz, is called the constant torque region because the motor produces a constant torque in the speed range, as shown in figure B. This is the same torque that the motor has at its normal 60 Hz operating speed. The region above 60 Hz is known as the constant power region because even though the torque is falling off, the speed is increasing, so the actual mechanical power stays the same. Power is the product of speed times torque. Commercial motor control circuits are capable of meeting these qualifications. Vector drives are based on the principle that the current driving an AC induction motor can be divided into two components: the current that produces the magnetic field flux in the stator and the current that creates the torque that causes rotation. The actual motor current is the vector sum of these two currents, and if they can be independently controlled, it's possible to drive the motor at full torque at any speed, right down to 0 Hz. There are three types of vector drives: sensorless vector, flux vector, and field-orientated control drives. We will discuss the field-oriented control drive first, because it's the newest and provides the most control. A block diagram is shown. First, you should realize that the motor can be any standard induction motor, but the drive is a very sophisticated microprocessor-driven feedback control system. As you can see, the motor itself is driven by a variable frequency circuit. Current sensors on the motor leads feed a current resolver, which identifies the flux-producing and torque-producing currents in the motor. A position sensor mounted on the shaft provides position and speed information. The drive electronics uses all this information to maintain two independent control loops: a speed-torque loop for control of the motor speed and torque, and a flux loop for control of the constant magnetizing stator current throughout the motor speed range. By maintaining a constant stator flux, the motor is capable of providing a constant torque from its base frequency 60 Hz all the way down to 0 Hz. The speed-torque loop is able to determine what the moment-to-moment slip is. Some slip is necessary for any induction motor, and then compensate by adjusting the rotational speed of the field very precisely with the windings so as to make up for the slip. This process can keep the motor running at exactly its set point speed, regardless of the torque demand. The outputs of both the flux and the speed-torque control loops are combined in the vector rotator to produce a single set of three-phase voltage waveforms. These waveforms are converted into PWM and fed to the transistors in the variable frequency generator. The sensorless drive predates the field-orientated control drive and cannot provide such precise control. As the name suggests, it does not require a position sensor, but instead makes guesses based on current feedback and what is known about the motor. This system is adequate for many applications. The flux vector drive does require a position sensor and maintains better control than the sensorless drive can, but not as good control as the field-orientated drive. This system estimates the flux producing and torque producing currents, vectors, in the motor and uses this information to control the motor. Flux vector drives can function effectively down to 2 to 3 Hz. This ends our look at AC motor control.